Now let's turn to our final presenter of the day, Andreas Dilger, who is with Whamcloud, a CTO there, and the Lustre Principal Architect. So he knows a lot about file systems. And we're going to dive just a little deeper than some of the previous conversations we had into what's coming up in the next releases. Welcome, Andreas.
Thank you. Today I'll be talking about work that we've been doing over the last year for accelerating workloads in a variety of application environments. With a lot of different applications coming online, we're not just doing traditional HPC anymore. There's a very wide range of applications, and they stress the storage in a number of different ways. Like it says, some applications have multi-terabyte data files or data sets that have very high read and write bandwidth requirements, while other workloads, you may have many millions of small files, 128K, 64K or less in genomics and machine learning and finance. And those all need to work equally well with the storage system. Large financial simulations that we've been working with may create 100 million or more files just in a single run. And so just static segregation of those applications across metadata servers is not sufficient. And as was discussed earlier with Selene, DGX systems are incredibly large for a single compute node, if you want to call it that. They have more than 100 cores and GPUs, multiple high-speed InfiniBand interfaces, and multi-terabytes of RAM we're seeing in a number of different applications. And so all of those need to be handled properly.
Now, in the past, Andres, I've noted and talked with a bunch of people that would be configuring Lustre, and it's been quite an academic exercise to customize and tailor it for any one of these workloads. Do you notice that increasingly people are running multiple kinds of workloads on the same systems?
Yeah, it's definitely happening more often because the cost of having a very large single compute node and a shared compute cluster, they want to drive the maximum value for their investment. And so not only are capacity systems running with multiple different types of IO workloads concurrently, but also even on the same single node, you may be having multiple containers or virtual machines running on the same piece of physical hardware, and they're running totally independent jobs. And so even from the point of view of a single client, from the file system point of view, they may be driving concurrent high IOPS workload as well as a streaming IO workload.
I was going to say, just from my perspective, that seems
So
like
one
that's
of the
getting more complex to manage the file system.
Yeah, and yet, the expertise of the users is, they're not specializing in I/O, and they want to get, a time to solution that's higher than, faster than, previously, and they don't necessarily have dedicated resources to assist them in optimizing the applications. They used to be in a traditional HPC environment where they would have an I/O specialist and they would spend many months or years optimizing the application. They want the storage to work out of the box, right, and to be able to leverage that to its fullest extent so that the application doesn't have to be tuned for the storage itself.
So go ahead and tell us a little bit about what you're working on here and what's coming up and what's really going to help the person focus on the science and not the storage.
Okay, yeah, there's a number of areas that we've been working on, and they're really focused on the three core tenets of a storage system. One is the the I/O bandwidth. Um, Second one relates to metadata performance, and then the third area that we've been working on is optimizing, how these large compute nodes that, such as a DGX A100, how they can, get a high performance from, just a few number of application threads running on that node. And so on the I/O bandwidth front, progressive file layouts is a feature that's been available in EXAScaler for a while. But what we're doing now is enabling this by default in all new installations that are coming out. And so, what this addresses is the mixed I/O workloads that you're seeing, with large data files sharing the same space with small, files that are containing annotations or other pre-computed application metadata. And you can't necessarily, in a traditional manner, optimize the I/O patterns for just large or small I/Os. As you can see on the right, um, with a large shared file that's being accessed by many clients, if you stripe that file over only a single OST, you actually have a quite low aggregate bandwidth. Versus if you stripe the file over all of the OSTs, you have a very high aggregate bandwidth, and that's great for multiple concurrent accesses. And the progressive file layout, has nearly the same bandwidth as the optimized widely striped file. But conversely, if you look at a metadata intensive workload where you're accessing a large number of small files concurrently, you're accessing file attributes, the stripe count one performance is highest, and the widely striped metadata performance is quite low. And yet with the progressive file layouts, we essentially have the best of both worlds. We're nearly at the peak performance for both of those, divergent workloads. And yet this is something that can be configured on the file system in a relatively straightforward way. And so that allows, users and applications to focus on, their own job rather than trying to, understand the details. And so this is actually, based on selecting varying layouts, file layouts for different sizes of files. And so as you can see, the LFS set stripe command here, you can configure this manually. This is the default that the file system ships with now. And so this segregates the file into a number of different regions. And so for small files, for EXAScaler, a gigabyte is still considered a relatively small file, but you have a stripe count 1, and anything smaller that down to 4K. But if it's over 16 gigabytes, the file will across 4 OSTs, which gives you a very high bandwidth. And once it's above 16 gigabytes, it will stripe across 40 OSTs. And the nice thing is that progressive file layouts are, they're tunable. And this is the file system wide default, but EXAScaler itself allows configuring this on a per directory or application basis, so that you can select these parameters that are optimal. But this is a very good out of the box default, and gives you it supports the wide range of application workloads already. On the metadata front, the other thing that's happening with new file systems is that you're getting an increasing number of metadata servers. And so for both capacity and performance reasons, you want to have multiple metadata targets to scale your performance horizontally. And so you can see, in a typical DNE environment, there's, the root directory is on MDT0, and you might manually create directories on other MDTs to balance your space. But this doesn't always happen, based on the experience of the admin and the people setting it up. So you want to make sure that this happens more easily out of the box. And so in EXA6, we're introducing a feature to automatically balance MDT usage across subdirectories, so that out of the box, you'll have a layout where the file system immediately starts using all of the MDTs, and you can do that through a round robin based selection policy. When the file system is empty, everything is in balance. They have 100% free space, and you'll round robin across the MDTs, but your usage in a certain directory tree may be heavier by user or project, or however you distribute the tree. And so if those become imbalanced, and the default 5% imbalance between MDTs, it will start moving new subdirectories over to the MDT with the most free space. It's not strictly that simple, because you don't want to put 100% of the load on one server and then 100% of the load on the other server, right? So it does it statistically, as you can see here, based on aggregation of the free inodes and the free space. It has a very low probability of putting, in this example, only 3% chance of putting new files or subdirectories on MDT0. But let's say MDT2 was newly added to an existing system. It has a lot of free inodes, a lot of free space, so it has the highest probability. And these weights are dynamic based on recent history and things like that. So it's just an example, but it gives you an idea of how things are balanced. And so this is the command that's run on the root directory to say that select the MDT based on -1 means that the servers are in charge of that. And then you can select how deep your round robin is among the subdirectory. So as you go deeper down, users will tend to stay on one MDT, because that gives you the best performance, and it gives you workload isolation and fault isolation. As well, another new feature that we've developed in EXA6 is limited layout inheritance. So if you do have a workload that doesn't agree with the out of the box defaults, which we do our best to accommodate a wide variety of workloads. But if you have something that needs its own tuning, you can say only do this for a couple of levels, and then it will fall back to the default. And so that really simplifies one of the pain points today. And finally, the other area that we're working on is optimizing performance for single nodes and even single-threaded applications. And so, traditionally, there was sort of the thundering herd of clients, essentially attacking the data server. And so you're really mostly focused on optimizing how the server was performing. But nowadays, with these large servers, you can have a considerable amount of bandwidth, 20, 40 gigabytes a second coming from a single node. And as a result, we need to be able to drive performance from a single client that is matching, what the server bandwidth can have. And so as you can see, one of the areas that we're doing is parallelizing workloads inside the kernel, so that applications, whether they're single-threaded or multi-threaded, they can take more advantage of the many cores that are available. And so we did this in a EXA5 already for parallelizing a file read ahead. And so we got a nice boost with the performance there. So no application changes, just double performance. And in EXA6 and upcoming releases, We're also doing further work to handle, high-speed Ethernet interfaces. InfiniBand is, I would say the preferred choice for high performance computing just because of the low latency and high bandwidth and CPU offload. But Ethernet is, the choice of many deployments. And so to improve that performance, we observed that getting multiple TCP socket connections really lets the single Ethernet interface, you know, use the many cores available, right? Because Ethernet does have a bit higher CPU overhead, and so you want to really be able to parallelize that. And so going up to 8 sockets per connection, we actually went, 1.7 up to 11 gigabytes a second. This was tested with a single 100 gigabit Ethernet, so that's essentially saturating the interface. And then the other area that we've done, even for single threaded application, doing direct IO, so no buffering. And typically, the direct IO is unbuffered and synchronous from end to end. So it's a little bit slower, but you get a little bit better, data reliability because you know that the IO is persistent as soon as you get the response. And we're able to parallelize this inside the kernel again, doing you know splitting up the data integrity checksums, reducing overhead on a per data per page and per RPC basis. And so, if you're doing 64 megabyte IOs in this case, we went from 700 megabytes up to 10 gigabytes a second, which is a dramatic speed up.
All right. So you've got auto balancing of really I/O performance with the parallel file layout. You've got auto metadata performance balancing with that feature, and here you've really provided ability to run off-the-shelf applications without having to really mess around terribly much trying to balance the threading performance. These are all coming in
Yeah.
EXA6.
Yes, there's still work that needs to be done in terms of, um, the connections per peer is currently static, and so we're working on, optimizing that to select, the best value based on the connection speed and things like that. So it's likely it will be an EXA6, but we crawl before we run. But these are all well underway.
Yeah, I mean, overall, this is really making this much more accessible and useful to the practitioner who's focusing on the work and not so much on the storage operation. So this is
Yeah.
really great stuff. Really appreciate it. Um, and I think that brings us to the end of our time here. So thank you, Andreas, for explaining this to us. I'm sure there's a lot more